Quantum is so interesting. I actually was on this stage 2 years ago, and then we spoke about the road towards a quantum internet. We're not there yet, of course not, but because quantum is always at least 10 years out. But today we move quantum a little bit into space, and I want to start actually with first thanking Michael and Reindert for the brilliant introduction into space and satellites and timing, because that relates very much to what we're going to talk about as well. So you might have seen a lot of announcements happening around space. There's companies thinking about building AI data centers in space. There's companies like the one I work for who are looking more into quantum tech, so building quantum key distribution on satellites and quantum entanglement on satellites. And it sounds still pretty far away, but actually it is actually getting pretty close. Some might recognize the person on this picture. That was actually me in 29. One of my other hobbies, except trying to figure out how quantum works, is hiking and mountaineering. And I actually tried climbing Aconcagua and Kilimanjaro. And that was my first exposure to satellites, or satellite communication, I should say. Back then, it was as if you would call someone really slow, lots of delays. It was really expensive. Like in 2009, I think we paid around $10 or 10 euros per minute to place a phone call. In 2019, it was actually a lot cheaper already. Still pretty expensive if you compare it to, obviously, GSM. But the fact is, there are locations where you don't have fiber. There's locations where you don't have coverage for cell phones. So satellite communication is there. Obviously, a couple of years ago, a lot of people thought satellite communications was maybe dying a little bit because of GSM. But there's actually a whole new market now arising with what I mentioned, companies looking into exploring space for different use cases as well. Little bit of an introduction, a few marketing slides. So I work for IonQ. For those who are not familiar with IonQ, we started off as a quantum computing company. So originally building quantum computers. At one point we did a SPAC, so now we're publicly traded. And when Nicolo became the CEO, a couple of years ago, he set out this vision for IonQ to become the full-stack quantum company. So next to quantum computing, we are in quantum communications. So we build quantum networks, quantum sensing, atomic clocks you heard about this morning, quantum in space, so the full spectrum. And that means that we operate in basically every layer of the network, from the ground to even underwater, where atomic clocks play a very important role, as you've heard this morning, for example, in submarines that cannot receive this GPS or GNSS signals, but still need accurate timing. For example, with Vector Atomics, one of the companies we've acquired, you can go blind from GPS for about 2 weeks and still have accurate timing available. Up to indeed in the sky, even in satellites. So we're putting these clocks on satellites, as you've heard this morning as well. And we're bringing quantum communications also into space. So that's basically for the marketing slides. Why is space becoming interesting? There's a couple of drivers. The prices to launch something, to build satellites, and to use one of the carriers to put your satellite in space have come down a lot. I don't want to say it's cheap, but we are at a point where if you have done like some funding, received some funding, you can actually already launch a satellite, especially the so-called cube satellites, the 10 by 10, very small satellites. You can put them on a launch vehicle as secondary payload, and that is relatively cheap to do. Obviously, the second point is sovereignty. As we've heard this morning as well, become less independent from GPS, but also for communications to become less independent from certain countries or suppliers. There's a lot of interest in that And you see that also with a lot of the initiatives here in Europe going on, with Eagle One, for example. Data and AI demand. You might have heard about a company named StarCloud. They are looking to build AI data centers in space. That sounds maybe a bit far out. But the interesting fact is that if you're in the right orbit, you have unlimited, basically, supply of energy, of power, right? And that's obviously one of the biggest challenges on Earth, to get enough power, right? Here, even here in Amsterdam, if you want to build a new data center, it's pretty hard to get a decent power connection. The second thing is cooling, right? In space, if you can radiate the heat out of the satellite, then you have unlimited cooling available. And the fourth one is that we are at a point where, in our case, obviously then quantum optics, but also other parts are becoming better available for space. So they're space grade, space tested, etc. So those are the four main drivers I see why space has become interesting again. As I mentioned, the pricing is probably one of the biggest factors. If you see 1981, that's actually the year I was born. It costed around $50,000, 54 to be exact, dollars per kilogram to put something in space, right? And if you imagine a Starlink satellite, for example, the smaller ones are around 250, 300 kilograms. So you can do the calculation how expensive that was. If we take that a few years later, when SpaceX started launching satellites with Falcon 9 and Falcon Heavy, the prices came down immensely, right? And as a matter of fact, they launch Falcon 9 now sometimes even twice a week. So last Monday there was a launch, and tomorrow there's actually another launch again. And they launch about 10 to 15 satellites themselves with one of these flights, but they also take indeed in additional payload. So you can basically just use them as a carrier to put your satellite or whatever you want in space. And the plan is when they are done with Starship, they're actually testing that at this moment, for the price to go down to even $100 per kilogram. So the economics are much in favor of bringing stuff in space. Here you can see another representation as well. What helps a lot here is obviously the reusability of launch vehicles, right? So the more you can reuse, the cheaper it obviously becomes, right? So that helps a lot. And the payload as well. You can see with Falcon Heavy, you can take 50,000 kilograms as payload. And that is a lot more than you could do in the past with Ariane and others from, let's say, the previous generation of launch vehicles. So what does it enable, right? What does it bring us? Well, the most famous example is obviously the Starlink constellation, but there's also Kuiper, which is now AWS, obviously, AWS Leo, and there's OneWeb. So it enables mega constellations. I mentioned Starlink releasing about 10 of these satellites with every launch. At the same time, they're taking about 5 to 6 satellites out of service again, right? The lifetime of such satellites is 5 or 6 years. So you need to constantly keep adding these satellites. We already mentioned sovereignty with Eagle One, EuroQCI projects, IRIS, etc. There's lots of interest in Europe, in Middle East, for example, as well, to launch own satellites, own constellations for precision, navigation, and timing, so GNSS, but also for observability, for example, right? Sensing has become so good that from a satellite you can basically read a newspaper on the ground. So you can make very high, precise images from space. AI compute, we already mentioned, basically because of the economics that work very well. Small-sat and CubeSat economy, those are the very small 10 by 10 centimeter cube satellites, which you launch to, for example, test if something is space-graded, if it would work in space. Typically a lifetime of a few months up to a year, just to test out some technology. In our case, quantum payloads. So, for example, QKD sources, which is a photon source with an optical terminal to transmit polarized photons from satellite to ground station. Use case for that is indeed quantum key distribution, for example. And with that, you enable also newer markets again, so in-space manufacturing and servicing. There's a lot of debris with all these satellites. There's potentially bigger satellites you want to build, so you spread them out over multiple launches, glue them together in space, like we did with ISS, for example. So space is becoming sort of a next layer in the networking stack. Again, as with the quantum network, we're not there yet, but it could be interesting to start thinking about adding space as a layer to your network. And even, for example, for an internet exchange, at one point you could consider using satellites to extend the reach of the internet exchange. I won't go too much into timing because we've heard that this morning as well. Something that could be a big driver for us as in the internet industry is obviously connectivity, right? Previously, you could do maybe up to a few gigabits of traffic per second if you were very lucky, if you have good connectivity, etc. Now, with the optical terminals, you can do up to 400 gig of data traffic, right? So from ground station to satellite and back, but also in between satellites. So that enables high-speed data for space. Compute we mentioned, quantum safe, for those who are familiar, quantum key distribution is a method to distribute key material in a quantum safe fashion, right? So you take away the attack vector of a classical and a quantum computer by using quantum physics. But the challenge of QKD is that you can only span like 100 or 150 kilometers in fiber. Obviously, with satellites, you can span much larger distances, right? So where in the past you would need trusted locations, so basically putting some of these QKD devices back to back, you can now span larger distances. And also quantum entanglement, right? We're also building quantum networks, and the practical distance you can span is only a few kilometers, which is not very useful, right? But if you can add space to that, you can span much larger distances. And quantum sensing, I mentioned, magnetometers, gravity, very high precise technology where you can detect, for example, submarines, where you can follow the changes of the tectonic plates. Very useful also for weather predictions and stuff happening. This was probably already discussed a lot this morning. When GPS goes dark, obviously this is a very relevant topic right now. GPS and GNSS systems, as we know them today, are indeed easily to interfere with because they're based on radio signals. But if you start using laser technologies, so optical beams, the band is much narrower, right? So it's much harder to interfere with that. So there's a couple of advantages of using space still as a backup to GPS, which is also in space. Why is this, what happened here, especially from a bandwidth perspective? As you can see, the early generations were very low bandwidth if you look at the data transfer rate. And actually around 2010, it became sort of usable, where we reached 100 megabits per second and 622 megabits per second. We're now at a point, as I mentioned, where you can actually do 100 and 400 gigs between satellite and Earth, and also between satellites. For example, that's what Starlink is doing. They use these laser optical beams between satellites, and to downstream they use still radio because it's obviously sort of comparable to a cable network, so to say, right? You have many consumers using the same signal. If you would have your own satellites or dedicated satellite, you can use laser as well between the satellite and ground. And then indeed you can actually reach 400 gigabits. So what is the difference? Again, radio signals, that's how we've been communicating with satellites in the past so far. Obviously, as I mentioned, the beam is much wider, so it's easier to detect and jam the signal. Again, it's very comparable to how a cable infrastructure, a broadband cable infrastructure works. Ideal for many users, like in Starlink example or GNSS example, but downside is indeed it's easy to jam. With optical laser communications, we can reach much higher link speed, and the beam is much narrower. In other words, it's much harder to interfere with the signal. Right? In space, it's really hard because you really need to get in between two satellites. But obviously also on ground, if you want to interfere around one of the ground stations, you probably won't be able to do that that easily unnoticed. And another thing which is interesting is that radio is highly regulated and optical is not. So it's much easier to communicate over laser because you don't need to go through all the approvals and regulations, etc. AI clusters, again, why is this interesting? Basically unlimited availability of power. As long as you have enough solar panels, you can get power from the sun, basically. And the interesting thing here is that in space, solar panels tend to be much more efficient than on ground, right? You don't have less, let's say, pollution, there's no clouds and stuff like that that interfere. So the efficiency of the solar panels is much higher as well. Cooling is basically unlimited available as long as you can radiate, right? There's no air cooling available because there's no air. Obviously, we're going to run into issues, you already see them, where folks start complaining about these massive data centers, very ugly big buildings, etc. You don't have that problem in space as well. I already touched on this a little bit, why space communication is sort of easier. In fiber, you have a lot of loss, right? And in classical communication, we've solved that problem with repeaters, with amplifiers, etc. For quantum communication, that is a bit more difficult because today there are no repeaters, right? There's work going on with quantum memories that could lead to quantum repeaters, but we're not there yet. So currently, you cannot amplify a quantum signal, a polarized photon, because if you, let's say, touch that photon, if you do something with it, the quantum state changes, so it becomes unusable. In space, you don't have the problem because there is, in near vacuum, you don't have any loss, basically, right? So whereas in fiber, there's an exponential increase of loss if you span a larger distance. In space, you don't have that problem, so it's much easier, again, for example, for quantum computers, if you want to connect them with quantum entanglement networks and QKD, etc., to use satellites for that. Also, because in many cases, there's not even fiber available, right? If you have a forward operating base somewhere in the middle of a desert, or you have a ship that's somewhere on the ocean, you're never going to have fiber available anyways, right? So basically, space is the only answer there. I think we touched on this already. The challenges of QKD you can overcome again with space because you don't need fiber. And as I mentioned, there's already a lot of these experiments going on, mainly indeed funded experiments, so whether that's indeed in Singapore or Germany or the UK, and now in Europe as well with the Eagle One project. There's a lot of research funded, which is really good to develop the technology. And now you see the first companies, including ours, to actually start developing commercial solutions to offer this to you and customers in space. Quantum sensing, I mentioned, very useful for predicting weather, for monitoring what's happening on Earth. In that sense, as I mentioned, the movement of tectonic plates, what is happening undersea, etc. You can actually do that from space. Very quickly on the technology, a brief overview of the TRL levels, the technical readiness levels of the different components. You can see the majority is in the green already, right? So the technology is there. A lot of components have been tested in space as well. And now it is up to companies and those interested in developing that technology to build it together and actually start building these constellations. So what does it mean in our case as network architects? By the way, I hope I can still say I'm a network architect because previously I worked with Juniper. So for us, it means that we can start thinking about adding space as a layer to our infrastructure, right? As I mentioned, if you want to spend those larger distances with high bandwidth, high capacity, space becomes an actual option. Whether that's via a shared medium, a Starlink or others, or maybe even dedicated satellites or ground stations, etc. And again, indeed, for policymakers, the sovereignty of, and cyber resiliency, as we were discussing here as well, and Gijs Tuinman mentioned yesterday, it's better to add more layers for redundancy and resiliency, so at least you have a backup in case your terrestrial network fails. I'll skip this one in the interest of time. There's one slide I want to show you this. Obviously, space means really nice pictures. This is from the Falcon 9 launch last Monday, where the actual rocket is passing the moon. So yeah, so just a nice picture. Thank you very much.
Space, the final frontier. Yes. Yeah.
Right.
Any question? Yes, I see a hand there. Tobias. Oh, you actually, I thought you were sitting there. You are now in the audience. Ah, you switched. Good for you.
Sorry, Tobias Wiewich, TU Wien, didn't know that I had to stay over there.
No, go for it. No.
I would like to know how this technological process interacts with the Kessler syndrome.
Sorry, one more time?
How that plan, agenda, technological process interacts with the Kessler syndrome.
With what?
With the customer?
With the Kessler syndrome. Oh, it is a description of the state of an advanced civilization able of spacefaring, where the orbit gets so clouded that the increasing of material, which leads to like basically an exponential growth of debris, which is uncontrolled,
right,
which at some point makes that civilization unable to be spacefaring.
Right, good question, and thanks for the explanation.
Yeah, whoa.
So as I mentioned, especially for example Starlink, they decommission quite a lot of satellites actually already, which they take out of service because if you launch a satellite, you do that with the intent for it to live for a certain amount of time, right? A few years in their case. So what they try to do, as long as they can indeed communicate with the satellite, is try to steer it into the dampkring.
Dampkring, sphere, hemisphere.
Yeah, hemisphere, thanks. And so it basically burns up there. But yes, there is definitely debris in certain, let's say, popular orbits. And that's why I mentioned there is actually companies who are now indeed looking into how can we clean that up again, right? So there's a second sort of economy starting to arise because of all these companies launching satellites. But it's definitely a concern. There's definitely orbits that are pretty busy. And there is official, a platform, I can't recall the name, that keeps track of who launches what into which orbit to avoid indeed a collision of satellites, which leads to more debris. But that is still, let's say, in the works. Not everybody adheres to it, and so it is an actual problem indeed. That's a good point, yeah. That's a challenge.
Creating rumble in space. Right. Should try to fix that. Right. Final question before we go to our final speaker of this. Yes, here we go, sir.
Hello, I'm Dave from AMS-IX. I have a question on intercepting signals. Is that also something that you're concerned with? Intercepting signals from any entity that has any potential harmful meaning about it? Is there anything, yeah?
Yeah, for sure. So, as I mentioned, with laser, obviously the band is much more narrow, so it's harder to intercept. And if you want to intercept between satellites, that probably cannot really go unnoticed if you fly something up there. And one of the reasons why, indeed, for example, quantum communication could become interesting here, because if you transport data in the quantum state, so using qubits, and somebody intercepts, then the state of the qubit changes. So you notice that somebody's interfering with the communication. And that is something you will never be able to do with classical communication. So yeah, good point.
Good point. Right. Give a warm applause for Melchior.
Thank you.
Thank you. Thank you. Nice.